A microservice is an application architecture that puts every application function in its own service. A microservice runs in its own container. These containers communicate using APIs. To understand microservices, let's start by understanding what a monolith is. So lithic is a Greek word that means stone. So monolith is one stone, like one block of stone. A monolithic architecture is a server-side system based on a single application. In a Java context, the whole application would be put into a jar, Java Archive Resource, or WAR, Web Application Resource file, and deployed to the server's production environment, the server production environment's Java runtime environment. So you would add those jar or WAR files to the class path. Advantages of the monolith: they're easy to develop, deploy, and manage. But there are some disadvantages with a monolithic architecture we need to understand to motivate the need for microservices. Now let's look at a simple example and compare how it would work in both a monolithic architecture and a microservices architecture. So our example here is an example of a ticketing system. So somebody could buy sports or concert tickets maybe online. So we need a user interface, a reporting module, inventory to know what tickets and what seats are sold or available, recommendation engine, you know how that works, right? AI and machine learning might recommend other events to somebody based on their purchase history, payment processor, PayPal or something, and a cart, a shopping cart to put their purchases in. So this might be an example of a typical ticket selling system. Now this is a monolithic architecture. A couple of disadvantages here. Downsides: adding new components requires tracking a huge number of details, and staying within the box of existing couplings is quite difficult. So we call this in IT the problem of heroic efforts, right? Our IT staff are really going to have to be on their A game to make this work. And another problem here, assuming we have a running system, right? It's working, it's in field deployment, and we want to upgrade it. So we have to take it offline on Friday night, and our poor IT staff, which is actually us, so we should sympathize with them, has to work basically day and night for a couple of days, and hopefully by Sunday evening get it up and running again if there's any problems. Once again, we're making heroic efforts to get it going. And we have another problem here because remember, all of these guys, they're all tightly coupled. We talked about the goal of we want low coupling, loose coupling, and high cohesion. Here we have the opposite. We have tight coupling with other components and with system libraries. So if we make a change, we have to track what dependencies are going on between these components and between the system libraries. And we also have the problem of scaling, which is one of the questions in Lab 4. If one component goes down, the whole application will crash. Now let's see how we might work with this in a microservice context over here. So again, we have our same components: user interface, right? Payment processor, our reporting application, inventory, recommendation engine, and cart for purchases. Now here, each one of these Java classes, or it might be a little application of several classes, but they are all small little applications, all of which are running where? In their own Java virtual machine. Maybe on different computers, right? Maybe even on geographically separate locations. So imagine maybe you are coding up a system for supporting a rescue, some sort of emergency relief thing. If there's a hurricane or something in one city, we might want to back up all of that data. When they go and find people they rescue and stuff, you would want that information physically available in another city. So if that city gets hit by a power failure, there's what they call failover scaling. So you're storing stuff in different geographies. So the concept here with microservices is each Java class or little application of several classes is running on its own JVM. ideally even on separate computers. Why? Well, let's look at our presentation component here. If our user interface, suppose some really popular performer comes. Suppose they sell tickets. People can go and listen to me talking about enterprise modeling, and word gets around, and soon millions of people are logging into the website because they want to buy tickets to hear me talk. So the system is going to crash, right? The whole system over here in a monolith, the computer goes down, and then if we identify the problems with the user interface, maybe we've got a couple of good developers on call, so they can go in and scale up that component. And if it is microservice, they just have to replace that one component. Why? Because it observed the pattern of high cohesion, low coupling, loose coupling with the other components. We can search and swap, right? We can just physically turn off the computer that guy is running on and just go to the configuration files, change the IP addresses to point to another computer, which is much more powerful now. Maybe we go to Amazon Web Services or Google Services or something, and we buy terabytes and terabytes of storage and lots of high power CPUs. Yeah, we'll pay for that. It'll be expensive, but who cares? We can keep the business running. So let's iterate over this once more now. So monolith, everything is running in one JVM. All of the components are tightly coupled with each other, highly dependent on each other's implementations, as well as a tight dependency on the underlying platform. Very bad design and problems. Well, scaling is one, as we just discussed. Another thing now, another advantage with microservice, it's very easy to iterate. That means to frequently make updates to our little microservice applications here, because I can just update the cart component and push it into my DevOps pipeline, and then my DevOps team is going to deploy, right? They're going to, maybe if necessary, the most they have to do is change some configuration information in these other components, and then at a certain time, maybe midnight, we just turn off one computer, turn on the next computer, and have that servicing up that component. So easy to iterate, easy to maintain, independent scaling, which achieves our SOA quality checklist of reducing risk. Okay, so let's talk through this one more time now. Your brain should be pretty warmed up here. So now let's start with a microservice and see why it's good, and then we'll just go back once more and see the corresponding disadvantages in the monolith. Microservice, we have each service, right? And think about our work in unified process with use cases and business processes. So we might have one microservice per business process. Each component is running on its own host, potentially even several computers. As you saw in your course on distributed computing, you might have several computers functioning as one unit, and there's mirroring and failover between them. If one goes down, the others will pick up the slack. And each of these is running on its own node or cluster. Advantages, easy to scale. If I start getting millions and millions of hits on my website, the computer, which is running my user interface, can just requisition from its server farm more. It can provision more CPU and more memory. And it's easy to iterate, meaning to push changes out to one component. Because since I have loose coupling here, I can just update my inventory component, no problem. And everybody else is going to be unchanged. They're going to keep talking to the same method API calls they were talking to before. So that achieves scaling and reduces risk. Why? Because if we get inundated, right, if we get a huge uptick in people hitting our service, we can server provision more resource. And if we find a problem somewhere, or if we just want to do routine maintenance, we can update one component affecting nobody else in the process, right? So scaling here in a monolith, if one component goes down, the whole application will crash. And what makes it more, it's going to be more difficult to get it up and running, getting back to our concept of heroic efforts. Adding new components, huge amount of details, tracking, right? You have to have really good enterprise application integration records, as well as very good project management. You have to stay within the box of the existing components and track all of your dependencies. So those are all the downsides of a monolith. So these components have high coupling with each other in the monolith and system libraries. So if you make a change, you need to track. And you can do that with UML, but it's still a hassle, right? And the more stuff you have to keep track of, the more you are likely to break. So monoliths are language and runtime dependent, whereas monoliths over here, my user interface might be a web browser. I might have another user interface that's a mobile app screen, iPhone or Android. My data store might be SQL for a while, then I'll decide to go out and change it to another, a MongoDB or something. So anyway, all of that. Just watch this video a couple of times if you need to, but the core learning outcome here is monolith, tightly coupled, all running on one host, introduces massive source of risk, as well as diminishes our ability to support and maintain the product and recover from errors. Microservices, we have a number of sub-applications, which may be one or several Java classes each. Each one is running in their own JVM, ideally even on its own physical separate host. So that's it. Take that and think about it. And if you have any questions, ask about them in class.
It was the dawn of the third age of mankind.